Hello everyone, I'm glad to present our work, BAMF-SLAM, Bundle-Adjusted Multi-Fisheye Visual Inertial SLAM, using recurrent field transforms. My name is Wei Zhang. This is a joint work with my colleague Shen Wang, Xinliang Dong, Longwei Guo, and my supervisor Norbert Haller. For real-world applications such as mobile robotics and augmented reality, visual inertial SLAM systems are widely deployed. However, emerging industrial applications and new benchmarks pose new challenges, as shown below, and require increased accuracy and robustness of state-of-the-art visual inertial SLAM system. In this work, we propose to use multiple fisheye camera plus inertial measurement unit as sensor setup for robust tracking and efficient mapping to address the mentioned challenges. We divide our system into front end and back end. Our front end begins by taking multi-image streams and IMU measurements as inputs. These images are first processed by CNN networks to extract features. On new keyframe, the RFT network predicts the dense pixel correspondences between the keyframe pairs with common views. These predictions serve as the targets for the projection factors and weighted by the confidence values. On the branch below, IMU measurements are pre-integrated between consecutive keyframes. With enough motion, we conduct IMU initialization to establish the gravity direction, body velocity, and IMU biases. The key to our front end is the local bundle adjustment, optimizing jointly the vertex poses and the depth maps with the projection factors and IMU pre-integration factors. Note that we also compute stereo reprojection based on the extrinsic between different cameras. On back end, as all the keyframes leaving the front end window, we convert the associated dense correspondences into relative pose edges. Then we search loop closures by floor distances between all keyframes. We refine iteratively the pose and depth maps where loop closures are found and other areas constrained by relative pose edges. This approach we call semi-pose graph bundle adjustment, which is more efficient than full bundle adjustment, while more accurate than pose graph optimization. Note that since we utilize the full field of view of fisheye image, we are able to close the white baseline loops with just a little overlap. In the end, our system produces a globally consistent map. We validate the effectiveness of our system on 3 datasets. From TOM VI dataset, our VIO version achieves the lowest trajectory error, while the full SLAM systems reduce the error further down up to only 1 centimeter. On newer colleague dataset, our system achieves the lowest relative pose error. On Table 3, the HITI Oxford dataset, which is part of the HITI SLAM Challenge 2022. In this challenge, OCVIS 2 was the winning approach. Our VIO version finished with the 2nd place. After this challenge, we complete our SLAM system development, and the full SLAM result outperforms the winning approach. Now let me show more qualitative results on the challenges scenes. First is the low texture scene. Rapid motion scene. Construction site and dark scene. Narrow space in stairs scene. Thanks for your attention.